Hello and welcome to the Computer Vision Festival, hosted by the AI Accelerator Institute, a global community of over 400,000 AI leaders and practitioners, all striving towards one shared goal: inspiring the next generation of machine intelligence. With expert presentations on the festival agenda covering everything from space exploration on Mars to self-supervised learning, you're in for a treat. If you have any questions for our speakers or want to connect with them further, then ask away in the comments sections of the video and hear them answered at the end of each session in our live Q&As. If throughout the day you're loving the content, then be sure to check out the AI membership plans, where you can get access to exclusive content in the form of interviews, reports and articles. Access all areas passes to all past and future events. You can also join our Slack community, which is home to more than 2,500 fellow AI, machine learning and computer vision professionals, and is full of dynamic conversations and contributions. So if you're not already a member, come and join us today. Sign up using the link on the AI Accelerator Institute website. I want to say a massive thank you to all of our sponsors and partners for helping us to bring the festival to your screens today. Our amazing speakers for contributing some awesome content, and to you, our attendees, for joining us today. That's it from us, so go ahead, sit back, relax, and enjoy the festival.
Hi, and thank you for joining me in the Computer Vision Festival. My name is Sima Sabach, and I'm a computer vision researcher. I've been working in the field for the past 10 years, and I still get excited every time I hear about a new cool idea. This is exactly what happened when I first heard about flow-based generative models, which apparently have been around for a while, but most people I know haven't heard about them. So I did what anyone would do: deep dive into different types of generative models to understand their strengths and weaknesses. And today I want to share this with you. We will start by presenting the problem deep image generators are facing. Then we will go over the main idea of 3 families of deep generative models. For each one, I'll present the vanilla version both intuitively and from a probabilistic perspective, and finish with the inherent strength of each method and how different challenges are being approached. Deep image generators can be seen as artists. During training, they use many images to learn a model, let's call it G. And in inference, they start with random canvases and use this G to generate images that looks like the one they have seen in training. So what does this G function learning? Well, ideally, we would like the model to learn the probability P of generating an image X from the distribution of our training images. This way, we can just sample P to get realistic images. Meaning, we want to find parameters theta such that the probability of our model is the same as the probability of our training data. One way of measuring distance between probabilities is KL divergence. So we want to find the parameters theta that minimize this distance. We have 2 problems with that. The first is that we don't really know P of X, we only have samples from that. So instead of matching probabilities, we can maximize the likelihood of samples from our training data, assuming that the images are independent. And the second problem is that we can't compute the probability of our model, because this requires computing this integral, which is equivalent to going over all the canvases in the world, which is not very practical unless we use a probability model with a closed form solution. Each family of generative models has a different approach to handle this issue, and we'll discuss it in this talk. We can divide generative models to the ones that are using implicit versus explicit density. The main idea behind implicit models is that we don't really have to learn p theta x. It's enough to learn how to sample from it, and we'll see how GANs learn to do that. For explicit models, we have to solve the issue of computing p theta x. One approach to overcome this is to approximate the density and learn something that we can't compute. Variational autoencoders do that by evaluating a lower bound on the density. Another approach is sticking to an architecture where we can compute the probability. Flow-based models do that by defining a mapping function z equals f of x, such that p of z can be easily computed, and we can use change of variable rule to evaluate p of x. These 3 families have been developed in parallel, and you can see their progress from the grayscale images back in 2014 to the state-of-the-art high-fidelity images we have today. But it has been a long way there, and each family had its own challenges to face. Let's start with generative adversarial networks. GANs have 2 competing components. First, we have the generator, which is like the artist we have seen before trying to generate images of cats. His adversary, the discriminator, is like an art critic. It has a bunch of real images of cats, and given two images, he needs to determine which one is real and which one was generated by the artist. In the beginning, the artist doesn't really know how to draw a cat, so it's pretty easy for the discriminator to learn what a real cat looks like. This requires the generator to learn and train until it produces something that looks like a cat. Now the discriminator has to work harder to decide, but once it learns, it raises the bar again for the generator. This goes on until the generator becomes so good that the discriminator can no longer tell the difference. If we formalize this, our generator is a learned network G that produces an image given a random input, and our discriminator is another learned network D that, given two images, classify them as real or fake. This is being optimized with a minimax on the classification loss. The classification loss has two terms. The first is only affected by real images and maximized when they are classified as real, and the second term only affected by the generated images and maximized when they are classified as fake. The discriminator's goal is to classify correctly, so he tries to maximize this expression, and the generator purpose is to generate images that are realistic, meaning to fool the discriminator, so he will try to minimize this expression. Since they have opposite objectives, they take turns training. When G is being trained, D is being fixed, and we minimize the classification loss, and when D is being trained, G is being fixed, and we maximize the classification loss. In inference, we no longer need the discriminator, we just randomly sample Z to generate images. So let's go back to the probabilistic interpretations. Ideally, we said that we want to find the probability density model so we can sample from that, but we don't know how to do that. So the way GANs do that is by starting with randomly sampling from the normal distribution that is easy to sample from, and then they learn a mapping function using the generator that maps Z into the image space. And now that we have both the real and generated images in the image space, we can compare between them, but instead of comparing the probability distributions, we use a discriminator in order to compare the samples in the data space by classifying them and see if we can separate between the two distributions. And in order to learn the generator and discriminator, we use the classification loss to propagate the information. Next, we have variational autoencoders. Variational autoencoders are a type of autoencoder, so let's start with understanding what is an autoencoder and why it can be used as a generative model. With autoencoder, we start with an image, X, and encode it into the latent space Z, and then decode it back to another image, X tag. And this is being supervised with the reconstruction loss, meaning we want the input and output images to match. So why this can't be a generative model? Well, let's look at visualization of the latent space Z. Each training image is being mapped to a single point in this latent space. And if we sample from this exact point and put it through the decoder, we will generate the reconstruction of our training images. And if we sample from anywhere else, we will get something completely random. So we have two problems. The first is that we don't know where to sample, and the second is that we can't generate any new images. We can only generate reconstruction of our training images. So what happens with variational autoencoders is that instead of mapping an image to a single point in the latent space, we map it into a distribution with a learned mean and standard deviation, from which we can sample a specific Z and decode it to an image. And in addition to the reconstruction loss, we add another regularization term on this distribution. We want it to be as close as possible to the normal distribution, meaning having a mean of 0 and standard deviation of 1. And this combination of reconstruction loss and regularization term is called elbow, which is a lower bound on the probability of X that we wanted to optimize, and we'll see why this is true later on. So let's first understand why do we even need to regularize this distribution. So let's say we didn't, and look back on the latent space. Now each training image is being mapped to this distribution, so this is a blob in the latent space. And now if we sample from that, we get something that is similar to this training images. So we solved one problem and we are able to generate new images. But still, if we sample from anywhere else, we will get something random and we don't know where to sample. What happens when we regularize the space is that we basically push all these distributions together to be around the normal distribution. And now our latent space is much more complete. And if we sample from the normal distribution, it is much more likely that we will generate a valid image. This regularization also creates some order in the latent space. And now, if we want to, for example, interpolate between the triangle and the circle in the image space, what we can do is use the encoder to encode them into the latent space, interpolate between them in the latent space, and use the decoder on different points on this interpolation line to generate new images that interpolate between the triangle and the circle in the image space. Pretty cool. We only have one problem with what we said so far. The problem is that what we do during training is sample Z, and this sampling depends on the learned parameters mu and sigma. So if we want to learn mu and sigma, we need to backpropagate through the sampling, but we can't do that because we can't backpropagate through sampling. So what we do to solve that is use a reparameterization trick. So what we do, we add another variable xi. So now the only thing that we sample is xi instead of z. And we can backpropagate as usual through the mean and standard deviation because they're not sampled. And we don't need to backpropagate through this new variable because this is not learned. And this solves our issue. So this is how it looks during training when we train the encoder and decoder together by sampling this xi variable. And in inference, we just randomly sample z from the normal distribution to generate new images. So let's see what this means in our probabilistic interpretation. Ideally, in explicit models, since we can't learn p of x, we try to maximize this on our training images. And because we can compute that in VAEs, we approximate a lower bound using variational inference. And we'll talk what is variational inference in the next slide. In the meantime, I want to mention that since this is a lower bound and the lower bound in variational autoencoders is called an elbow, since when we optimize and maximize the elbow, it actually maximizes p of x as well because it's greater or equal to this lower bound. So what is variational inference? In variational inference, we have a hidden variable z from which we generate an observed variable x. And the goal is to infer the posterior, which is the probability of the hidden variable given the observed variable. And this is being achieved by this expression. And the denominator is something that we can compute by making some assumption on the generative process, parameterizing this by theta. But in the denominator, we have p of x that we know we can compute. So what we do in variational inference is instead find the best approximation of this posterior among a parameterized family Q phi. What does it mean? Let's choose, for example, a parameterized family of one-dimensional Gaussian. And in this case, the parameters phi would be the mean and standard deviation of this Gaussian. And we will find the best Gaussian to fit our data. So we replace the problem of inference of the posterior with an optimization for the optimal phi parameters. So we want to solve the phi parameters that minimize the distance between our approximated function to the real posterior. But wait, we still have this posterior in our expression, so how can we optimize for that? And it turns out we don't really need the normalized posterior. We don't need to normalize it by p of x. It's enough to use the denominator. Why is that true? If we look at the definition of the KL divergence and follow some very simple logarithmic math, we see that a scaling of this probability ends up to be a bias term in the KL divergence. And since the choice of our parameters and the choice of the model does not depend on p of x, this p of x only depends on the data, this is a constant in this optimization. So we can omit that and only optimize the denominator. So let's look at an example. So let's say we have a parameterized family of two Gaussian, mixture of two Gaussians. So now we have four parameters, two means, two standard deviations. And we start with this initial solution. So what we see here in blue is the non-normalized target distribution. So this is the posterior without normalizing in p of x. So this is the denominator we saw before. And the dotted blue is the normalized posterior that we want to find. And in green, we have our model initialized in random variables. What we can do in each iteration is compute the KL divergence. We map it into a distribution with a learned mean and standard deviation, from which we can sample a specific z and decode it to an image. And in addition to the reconstruction loss, we add another regularization term on this distribution. We want it to be as close as possible to the normal distribution, meaning having a mean of 0 and standard deviation of 1. And this combination of reconstruction loss and regularization term is called elbow, which is a lower bound on the probability of acts that we wanted to optimize, and we'll see why this is true later on. So let's first understand, why do we even need to regularize this distribution? So let's say we didn't, and look back on the latent space. Now each training image is being mapped to this distribution, so this is a blob in the latent space. And now if we sample from that, we get something that is similar to these training images. So we solved one problem and we are able to generate new images. But still, if we sample from anywhere else, we will get something random and we don't know where to sample. What happens when we regularize the space is that we basically push all these distributions together to be around the normal distribution. And now our latent space is much more complete. And if we sample from the normal distribution, it is much more likely that we will generate a valid image. This regularization also creates some order in the latent space. And now, if we want to, for example, interpolate between the triangle and the circle in the image space, what we can do is use the encoder to encode them into the latent space, interpolate between them in the latent space, and use the decoder on different points on this interpolation line to generate new images that interpolate between the triangle and the circle in the image space. Pretty cool. We only have one problem with what we said so far. The problem is that what we do during training is sample z, and this sampling depends on the learned parameters mu and sigma. So if we want to learn mu and sigma, we need to backpropagate through the sampling, but we can't do that because we can't backpropagate through sampling. So what we do to solve that is use a reparameterization trick. So what we do, we add another variable xi. So now the only thing that we sample is xi instead of z. And we can backpropagate as usual through the mean and standard deviation because they're not sampled. And we don't need to backpropagate through this new variable because this is not learned. And this solves our issue. So this is how it looks during training when we train the encoder and decoder together by sampling this xi variable. And in inference, we just randomly sample z from the normal distribution to generate new images. So let's see what this means in our probabilistic interpretation. Ideally, in explicit models, since we can't learn p of x, we try to maximize this on our training images. And because we can compute that in VAEs, we approximate a lower bound using variational inference. And we'll talk what is variational inference in the next slide. In the meantime, I want to mention that since this is a lower bound, and the lower bound in variational autoencoders is called an elbow, since when we optimize and maximize the elbow, it actually maximizes p of x as well because it's greater or equal to this lower bound. So what is variational inference? In variational inference, we have a hidden variable z from which we generate an observed variable x. And the goal is to infer the posterior, which is the probability of the hidden variable given the observed variable. And this is being achieved by this expression. And the denominator is something that we can compute by making some assumption on the generative process, parameterizing this by theta. But in the denominator, we have p of x that we know we can compute. So what we do in variational inference is instead find the best approximation of this posterior among a parameterized family Q phi. What does it mean? Let's choose, for example, a parameterized family of one-dimensional Gaussian. And in this case, the parameters phi would be the mean and standard deviation of this Gaussian, and we will find the best Gaussian to fit our data. So we replace the problem of inference of the posterior with an optimization for the optimal phi parameters. So we want to solve the phi parameters that minimize the distance between our approximated function to the real posterior. But wait, we still have this posterior in our expression, so how can we optimize for that? And it turns out we don't really need the normalized posterior. We don't need to normalize it by p of x. It's enough to use the denominator. Why is that true? If we look at the definition of the KL divergence and follow some very simple logarithmic math, we see that a scaling of this probability ends up to be a bias term in the KL divergence. And since the choice of our parameters and the choice of the model does not depend on P of X, this P of X only depends on the data, this is a constant in this optimization. So we can omit that and only optimize the nominator. So let's look at an example. So let's say we have a parameterized family of two Gaussian, mixture of two Gaussians. So now we have four parameters, two means, two standard deviations. And we start with this initial solution. So what we see here in blue is the non-normalized target distribution. So this is the posterior without normalizing in P of X. So this is the nominator we saw before. And the dotted blue is the normalized posterior that we want to find. And in green, we have our model initialized in random variables. What we can do in each iteration is compute the KL divergence between the blue and green lines and use our favorite optimization technique, for example, gradient descent, to update the parameters of our four parameters. And we keep doing that until we converge to the normalized posterior that we wanted to find, or at least its best approximation using this family of functions. Note that the choice of family of functions is really important. For example, if we choose a single Gaussian, we won't be able to feed the data well, no matter what we do. So what does variational inference has to do with variational autoencoders and evidence lower bound? If we look at the definition of KL divergence between the posterior and our approximation and follow some math, we get this expression. We have log P of X, which is our evidence, is equal to the elbow, which is the evidence lower bound, plus the KL divergence that we started with. And we know we can't compute that because we don't know what the posterior is, but we do know that this is measures distance, therefore it's always greater or equal to 0. And this is where the evidence lower bound gets its name. This is a lower bound on the evidence. And in the case we have infinite capacity for Q of phi, where we will be able to minimize the scale divergence to 0, and maximizing the elbow would be the same as maximizing P of X. The elbow has two terms. The first is an observation term, and we'll see how this relates to our reconstruction loss. And the second is a prior term, and we'll see how this relates to our regularization term. Let's start with the prior. The prior relates to the encoder, and in order to get to the loss that we know, we have to make two assumptions. The first is the probability of Z is normally distributed, and second is that our parameterized family is Gaussian with a mean vector of mu and a diagonal covariance matrix. This actually means that we assume independence between the different dimensions of our Z vector. And if we plug this in the KL divergence definition, we get this simple closed form solution that we can optimize during training. And if you notice, this is exactly our regularization term. If we look at the observation term, this relates to the decoder, and we make a single assumption here, that the probability of X given Z is a Gaussian, where the mean is the output of the decoder, and it has a constant variance across all pixels, so we assume that there is independence between those pixels. And if we plug that in, we get our reconstruction term divided by 2 times the variance. So if we put it together, in order to get to the loss function that we know, we basically assume that the variance is equal to half, but actually the variance C is actually a trade-off between how confident we are in the data and how confident we are in the prior, and we'll see later how we can use that for different benefits. Next, we have flow-based generative models. The architecture of flow-based models resembles the one of variational autoencoders, but it has some fundamental changes. We still have an image X that is being encoded into latent space and decoded back into the image space, only our decoder is called a flow and implements a function f, and the decoder is called an inverse flow and implements the exact inverse function. This means we don't really need to train the decoder. We can train a single network, the flow, and in inference we just invert it to generate new images. The other difference is that because we use invertible functions, Z has to be in the exact same dimension of X and not in a lower dimension like we use in autoencoder. So schematically speaking, it looks more like that. Z is in the same dimension of X, only normally distributed. These changes allow us to directly optimize the probability of real data, which is our holy grail. So let's dive in to understand what is a flow and how it is useful in the generative model. A flow takes X from a complex distribution and maps it into Z from a simpler distribution using an invertible function, so we can also go back from Z to X. We can use this mapping between X and Z to write the probability of X that we don't know how to compute as a function of the simpler distribution of Z. If we follow the change of variable rule, we get this expression that has two parts. The first is the probability of Z, which is our simpler distribution. And this is where the magic happens. This is where you decide what would be the distribution of the latent space. We usually use the normal distribution, but it can be uniform, Gaussian, or whatever is easy to compute during training. The second term is a scaling factor. All it does is making sure that this expression is still a valid probability distribution and sums it to 1. Mathematically speaking, this is the determinant of the Jacobian matrix of the transfer function, but although it looks scary, it's just a single number that normalizes the distribution. So let's look at a simple example. Let's say Z is equal 2 times X, and X is uniformly distributed between 0 and 1. Then our probability distribution looks like this simple nice square. And if we naively assume that P of Z equals P of 2X, we have a problem, because if this sums into 1, this will sum into 2. And it turns out that we need to normalize this, and this normalizing factor is exactly the Jacobian determinant, or in the case of one dimension, just the gradient of this function. So what are the conditions from this transformation function for it to be useful in the generative model? First, the determinant of the Jacobian has to be easy to compute. This is what we evaluate during training, and if this is slow to compute, training will be slow as well. Secondly, it has to be easily invertible. We are using a generative model, meaning we have to generate X from Z, so we need to use the inverse function. The thing is that in generative model, the distribution of X is the distribution of our training images, and we know how complex it can be. So what are the chances that we can find a single function that will map it to the normal distribution and still hold its conditions? It is much more likely that our training will be very slow. And this is where we use the last piece of normalizing flows. A flow is not a single function. A flow is a composition of functions that gradually transforms the complex distribution into a simple one function at a time. And the nice thing about composition is that the inverse function is actually a composition of each of the inverse functions. This means that it's enough for each of the intermediate functions to hold these conditions, and the whole flow would hold them as well. And the composition itself allows us to generate complex functions from simple ones. And now we can write the change of variable rule in this way, and each of this intermediate function adds us another element to this sum. Let's put it back in our generative model. During training, we learn a single network, which is a flow, and a composition of functions transforms in the neural network world into different blocks being stacked together. And we directly optimize the probability of real data using this expression. And in inference, we can use the inverse flow to either reconstruct X from Z, or to just randomly sample Z from the normal distribution to generate new images. And the inverse flow is the inverse blocks being stacked together. So let's review what we've seen so far. Until now, we discussed the vanilla versions. Now we want to understand the inherent strength of each family and the challenges it had to face from the grayscale images to where we are today. Note that this is not a complete list. I focused on a few topics since we are limited in time. The main strength of GANs right from the start was their high fidelity images. There's actually a whole website called This Person Does Not Exist, with images generated by StyleGAN, which is the last big breakthrough in GANs. As an implicit model, they have the flexibility that comes from not having to compute density, but it also comes with a cost, and some works are trying to estimate it. The main challenge is with unstable training and mode collapse, and we will focus mostly on that. Another issue that received a lot of attention is the latent space of GANs and how to control attributes in the generated images. And we'll talk about it briefly in a few slides. Formulation of the latent space also affects reversibility, which is knowing what is the Z value that will produce a specific image. One approach to solve this is by adding an encoder to the GAN. The problem with the original minimax GAN is that when the discriminator is correct and classifies fake images as fake, gradients to the generator are small and it's hard for it to improve. The solution suggested in the original paper was using non-saturating GAN to solve this by replacing the generator loss from being log 1 minus d to minus log d. And you can see that the gradients are indeed larger in this case, but they actually diverge. Another approach was proposed by Wasserstein-Gahn that gives informative linear gradients even in the case of distinct distribution by replacing the distance metric, as you can see in the light blue curve. The theoretical justification for the new metric required the function of discriminator to be 1 Lifshitz, which can be achieved by bounding the gradient magnitude to 1. Wasserstein-Gahn was the first breakthrough in stabilizing GANs. The original paper suggested enforcing Lifshitz constraint by gradient clipping of some hyperparameter C that is bounded by 1, but this was very sensitive to the choice of this hyperparameter and could result in divergence. Soon after that, gradient penalty was proposed as a better way to enforce Lifshitz constraint. It added regularization to the gradients of a random point between real and fake data point, and penalized gradients that are larger than 1. Next, in the paper Which Training Methods of GANs Actually Converge, the authors realized that the important part of the gradient penalty was applying it to the real data points, and that's what can stabilize non-saturating GAN as well. They used a zero-centered penalty, meaning trying to get the gradients to 0 and not just bound them by 1. In the same time, another paper was published that enforces Lifshitz by normalizing each layer by its spectral norm instead of adding regularization. They show that this can be implemented more efficiently than gradient penalty. The different loss functions were evaluated in the context of mode collapse, and this paper made 2 important observations. To avoid mode collapse and stabilize training, first, real data points have to be a local minima, and the wider it is, the more stable we are. And second is that forgetting what we learned in previous iteration is a big problem, and added memory helps in mode collapse, and we'll talk about it in the next slide. For example, you can see that in this example of mode collapse, in each iteration we forgot the mode that we had in the last iteration, which is a problem. Let's see an illustration of this problem for non-saturating GAN. In this image, blue points are the real data points, the red points are generated points, and the arrow showed the direction and magnitude of the gradients. You can see real data points are not a local minima for the loss, and therefore fake data points are not drawn to them. Moreover, if you look at the green square, all of the gradients are in the same direction, so we're not pointing fake data points towards different modes. So when we get to iteration 20,000, we basically went back to where we started. But if we add some memory to what we solved in the previous iteration, like adding momentum to the optimization or using the atom optimizer, we can avoid mode collapse. However, this is still not a stable solution because real data points are not local minima. On the other hand, in R1 regularization, we make real data points local minima by enforcing the gradients to be 0, and you can see how this converges nicely to a stable solution. This consistent regularization over time can be seen as adding memory. Other contributions to the stability of GANs stem from architecture. In particular, ProGAN stabilized training by progressively growing the GAN, which is similar to coarse-to-fine approach in classic computer vision. Taking this a step further, MSGGAN added skip connections between encoder and decoder of the same resolution, which stabilizes training even more. It's interesting to know that the authors of StyleGAN are the same author of Progressive GAN, and this was the architecture they used in the first version of StyleGAN. But for the follow-up paper, StyleGAN 2, they actually switched to MSGGAN. Next, let's talk about disentanglement. If the features are disentangled, adding sunglasses, for example, will not change anything else. But in this example, you can see it changes skin color and background as well. This means that the features are entangled. StyleGAN explained why entanglement happens in a very nice visualization. Let's say we have 2 disentangled features, but there are some combination of them that do not appear in the data, like you can see in figure A. Since we are sampling from the normal distribution in figure B, we need to close the hole and features become entangled. What they propose is to learn a mapping to an intermediate latent space that can be disentangled, and therefore separate the sampling from the latent space that we actually want to use for disentanglement. A follow-up paper actually shows how disentangled this latent space really is and how changing a single dimension has an effect on a single attribute in the image. There are other approaches to generate this intermediate latent space. For example, splitting the generator and discriminator into two networks and encouraging them to use a mutual latent space by using an autoencoder, or by using flows to map the Gaussian prior into the real prior of the data, which showed amazing control on the fine details in the image. This work is called style flow, as a reference to style GAN, and it actually shows how to control these kind of features even better. Next, variational autoencoders. One of the nice benefits of VAEs is that they are easy to train and show nice convergence. Also, while this is not guaranteed, they tend to have a disentangled latent space compared to other methods. This is being encouraged by the assumptions we made on the model, and in particular, the prior that we chose with the diagonal covariance matrix that assumes independence between different dimensions of Z. The main weakness is blurry images, and we will focus on that. One explanation to the blurriness is that latent space is not expressive enough. For example, the dimension of Z is too small, or if the prior isn't a good assumption. In this work, they tried to learn the real data distribution and got some improvement in the generated images compared to other priors. Another explanation that stems from our assumptions is that the output image is the mean of the decoder, and it has a variance of C, which is the trade-off between our prior and observed data. The smaller the variance is, the less blurry the image will be, in theory. However, we added regularization for a reason, so we can't make it too small, otherwise we will lose all the nice benefits in the latent space. This work learns the optimal weights and shows improvement over the vanilla VAE in the sharpness of the images. A similar observation was made by this paper, only they say they don't need to learn this weight, they have a heuristic to compute that. In this context, I also want to mention beta VAEs that use the same trade-off to increase the variance in order to make the prior stronger and achieve better disentanglement. In this image, you can see the results of trying to change the rotation of the head. In beta VAE, this is the only attribute changing, which is not the case in the VAEs where we change identity as well. Another approach to improve the fidelity of the images is to combine VAEs with GANs or other adversarial losses, and by this achieve the best of both worlds, both high-fidelity images and the nice properties of the latent space. There's only one paper I could find that generates high-fidelity images without adversarial loss, and this required a lot of engineering, and there's no one cause for their impressive results. And we came to our last model. The main strength of flow-based models is the exact estimation of the likelihood, which also comes with exact reversibility. They can also generate high-fidelity images and show impressive disentanglement and interpolation in latent space. This GLOW paper was actually the one that inspired this talk and got me interested in what flow-based models are. Their main challenges comes from the fact that they are invertible. This restricts the architecture and may cause slow training. Also, the architecture has to stay in high resolution in order to be invertible, and this brings a challenge with scaling up that is yet to be resolved. So let's talk about the blocks used by this GLOW architecture. The first two are pretty straightforward, either applying a scalar bias or multiplying with a weight matrix. I want to focus on the third one that uses a nice trick. The first half of the tensor stays untouched, while the other half is being transformed. This creates a nice lower diagonal structure in the Jacobian matrix. And since we only care about the determinant of the Jacobian matrix, this makes it easy to compute because we only care about the diagonal terms, and we can see that our log determinant here gets to be just the sum of the log scales that we apply. Another approach to handle the issues with flows is not to use a flow for the full architecture, but to combine it with other methods. For example, using it with VAE architecture to directly optimize P of X instead of the elbow, and you can see that it shows relatively nice results compared to a VAE. Or, as we saw before, combining this with GANs to control the latent space. To summarize, we've seen three types of generative models, and their approach to generate images from the distribution of training images. State-of-the-art papers are able to generate high-fidelity images with all three types of generative models, but each family had its own challenges. GANs had to focus on stabilizing training and avoiding mode collapse, and also on disentanglement in the latent space in order to control the generated images. Variational autoencoders focused mostly on improving the quality of the image and avoid blurriness. And flow-based models had to work through the downside of having an invertible function and find a way to scale up the architecture, which is still an open challenge. The vast research on GANs helped them overcome most of the challenges, and I hope that to see this happens for flows as well. So which one will you choose? Feel free to reach out and tell me what you think or ask questions. Thank you for your time and enjoy the rest of the festival.
Hey there, everyone. Welcome back to day 2 of the Computer Vision Festival. Glad to have you all back in the house. Some of you, it might be your first time. I'm sure a lot of you attended yesterday. I can see a lot of familiar names. And yeah, thank you so much for that presentation, Sima. Really, really cool presentation. I think the audience loved it. You can tell by all the comments in the comment section there. But yeah, why don't we open up the floor for some Q&A?
Sure.
Cool. So we could jump in with a question. Cool. Yeah. First question from Juan is so a bit of a starter question. What starting methods do you recommend for computer vision starters?
I'm guessing he meant in the context of generative models, and my best recommendation is to find a problem that is most similar to yours and start with that as a baseline. And this is true for actually anything in computer vision, because you don't want to overkill with the best thing, even if it's more than you need for your problem. Always stay with something similar to what you're trying to solve.
Okay, perfect. So hopefully that helps you out there, Juan. And the next question is from Jay Seal. Glad to have you back. Welcome to day 2. So GAN can only generate images from the distribution of input images. Is it possible to generate images that are generalized from the input images, something that normal data augmentation would do? To be precise, we can use GAN for data augmentation for the data deficiency problem. I can repost that in the chat, Sima, so you can have.
I saw that. Exactly where you are. You won't be able to generate things outside the distributions, because then the discriminator would know that this is not the same. It would be able to really easily classify them as fake. It is able to generate new images from the same distribution, though.
Okay, cool. Great answer. So hopefully that helps you out, Jaysil. And next one for Moreo. She says, hello, Simon. Can SVMs be considered as autoencoders since they do some sort of encoding of the input data to another dimensional plane?
So from what I remember for SVMs, it's more of a classification method. Maybe you mean using the kernel method to change to a space where you can solve this problem linearly, but this is not an autoencoder. It is sort of a mapping for this classification, but autoencoder takes an image, encodes it to a latent space, and reconstruct that, and SVMs don't do that.
Okay, well, there it is. And Pankaj, so with the compositions and the chaining of the flow functions, does one need to be careful about numerical artifacts?
Yes, this is a really good observation. If there are numerical artifacts, you will get reconstruction. You won't get an identity.
Cool. There you go, Pankaj. So, Sean, that's a question about the slides. I think we've got a couple more. So, how do you all plan to use generative models for solving market problems?
I don't know how to answer that. What do you mean market problems?
Maybe Prasanna, you can elaborate a little bit there, but we'll move on to the next question. So Amatia, so which generative model is known to generate better latent features? Are certain generative models better for certain usages? If so, could you state some situations?
So in general, GANs don't use an encoder. There are some variations that are able to do that. But if you need something that will encode any image to the latent space, then you probably need to use variational autoencoder or a flow. I would start with variational autoencoders because this is less restricted. But maybe you don't even need a variational autoencoder. Maybe autoencoder is enough if you only need the latent features and not to generate anything.
Okay, cool. Well, thanks for your question, Amartya. And then we will move on to Mahendra. So down at the bottom there, Sima. So can I use these models to identify attacks done through images? How can I identify a bona fide versus spoof images using these models?
So I'm not that familiar with all of the details. I know there is a lot of research there, but you will be able to compare between these distributions. For example, if this is a natural image or not a natural image, but a lot of those methods actually go through the actual features of how the network learns and are able to fool that. So I'm not sure. It depends how advanced the attacker is. Some of them you can, but some of them will be able to fool you.
Okay, cool. So hopefully that gives you some help there, Mahendra. Gisal, so they're saying, I'm looking forward to using reinforcement learning as a replacement of detector in GAN architecture. Any views on this / any mathematical challenges?
Unfortunately, I'm not, I don't know reinforcement learning well enough to answer this question.
Okay, cool. So we'll move on then. So Pankaj, I think that's in reference to Pankaj's first question. So the first question was with the compositions and chaining of.
Yeah, you can call it an autoencoder because it brings us to a space where everything, well, it sort of disentangled everything because it's trying to go to the agent values, to the different, I forgot how it's called in English. Sorry about that. So yeah, it's sort of an autoencoder, although I didn't think about it in this context.
Okay, and then so yeah, sorry, Prasanna, I may have got your a question wrong. That was a question to the audience. So why don't some of our fellow participants jump in and answer Prasanna's question there if you have any insights. But next question for you, Sima. What other distributions other than normal distribution can we use for modeling as well as sampling? Does distribution necessarily have to be symmetric?
So, well, first of all, it depends on the method. I think most of them show that the normal distribution is not a good distribution for generative models, that it's better to transform it to a space where this is disentangled. But the main idea, the reason people use normal distribution is because it's easy to sample from. So you can choose anything else that is easy to sample. It doesn't necessarily have to be symmetric. It's just, I think, usually easier to sample from symmetric distributions.
Okay, nice, perfect. And on that note, Sima, I think we can wrap it up. What a great way to kick off day one. It seemed like the audience loved your presentation. We've loved having you here as a speaker on our virtual stage. You're invited back to any of our events anytime you like. It's been a pleasure. One last question from Pankaj, why not? But does it help that the distribution is in the exponential family? What's your thoughts on that?
I'm not sure I followed, but feel free to reach out to me offline on LinkedIn and I'll try to answer that.
Cool. Yeah, Pankaj, you heard it. So find Simra on LinkedIn, or you can do it through our website. We've put her LinkedIn up there.
Also, in the handout, you have all of my contact information in whatever platform that you prefer.
Cool. So that's pretty much all we've got time for. Gisol, same as you. If you can follow up with Sima with that question. And what we'll do, we'll move on to the next session now, which has already kicked off. It's a really cool session. Computer vision for exploring Mars from our good friend Ryan Alimo. He's a computer vision researcher at NASA JPL. Keep your questions coming in, but let's carry on that conversation over LinkedIn. I'm gonna post a link to the next presentation now on the chat. But Sima, once again, a huge thank you, and thank you to our audience for tuning in. I'll see you on the next session.
Thank you for joining. Bye.
Bye, Sima. Take care. Bye-bye.